So yesterday we managed to cover a huge amount of ground. So I'll just go over, just remind you of a couple of things that we did. So first of all, there was this idea that if you're able to write down the, well, I can hear something. If you're able to write down the thing you're interested in this kind of form, right? Then there's this very useful thing that the mean value of z is just n times the mean value of x, and the variance of z is n times the variance of x, right? So it's means add and variances add, and we use this for a few different calculations. So you've seen the same thing being used in many contexts. So one of them, we talked about a random walker who's on some sort of grid, and these grid positions are separated by some distance delta, and if you're sitting over here you can jump to the right or jump to the left. So this is some x, right? And the total, the histogram that we made for x was at minus delta and plus delta. So the mean value of x was 0 and the variance of x was delta squared, and then we use this to calculate how far the thing goes over time. The other calculation we did was, we said if we take a fixed time interval and break it up into small chunks of size delta t, and if there's a probability p that something happens, so here you get these spikes, right? These spikes were meant to be deterministic, or sorry, discrete events that happen in some continuous space. We were talking about molecules in the flask, we would talk about stars in the sky, or whatever it is. And in this case, the relevant histogram was x could be 0 or x could be 1, and it was 0 with some probability 1 minus p, and it was 1 with some probability p. And then we added this up. So after n steps, we found that so this is a binomial distribution, right? After adding n of them, right, this individual one is a Bernoulli variable. So if again z is the sum of all these x's, then we found that the mean value of x was np, and the variance, sorry, mean value of z was np, the mean value of z, the variance of z was np on minus. So the point about all this is that you don't have to do too much complicated mathematics to understand a lot of what's going on if you just remember this relation. Okay. So today I'm going to cover, so I'm deviating from the syllabus that I had written down when I was asked to contribute to this workshop. I think the other lectures you're seeing already give you a good idea of using differential equations, some ideas about networks and so on. So I'm going to be sticking to these kinds of ideas, probability and using probability in models of, simple models of living systems. Okay. So these things obviously are all connected, and they have this underlying idea, but today I'm going to teach you a way to think about systems like this, right, which can move around randomly, and we're going to use a framework that I'm going to teach you to understand what happens when a gene is expressed inside a cell. Okay, so it's a real biological problem, and we're going to build some mathematical tools to answer that question. So the biological problem, right, it's very simple. So gene expression, right, or just transcription. Right, so you know that you have DNA, and on the DNA there will be some molecule called the RNA polymerase, which moves from some starting site and will scan over a gene, and when that happens it releases this strand which is called the messenger RNA, and the messenger RNA has a binding site for another thing called the ribosome, and the ribosome scans the messenger RNA, and what comes out of that is a protein. Okay, and so we want to understand this very simple thing, right? So you think there's not much to it, but actually there's quite a lot to it, and I'm only going to focus on this piece, which is the process by which you have a gene and you make mRNAs. And to start off thinking about this, okay, I need to tell you what processes happen, right? So let's assume that once the RNA polymerase is finished reading the gene, that's when the mRNA strand gets released and it goes into the cytoplasm of the bacterial cell, let's say, and that's when I count it as being a single mRNA. Yeah. Now, once the mRNA is in the cell, it can actually be destroyed, and the way it gets destroyed is some other protein will come and start eating it from one side or from the middle, and eventually it will just completely break up the RNA back into its individual nucleotides. Okay, so there is a creation process and there's a decay process. So just to take that picture and then compress it down, so you have some DNA at some rate alpha, you make the mRNA, and with some rate gamma, you destroy the mRNA. Okay, and this is all happening inside a single cell. So if you, I won't get too much into the details of how good or bad this approximation is for now, but if you had to write an equation for this, right, the easiest way to start is just to think of these as chemical reactions. Okay, so inside a cell there will be some concentration of DNA. Yeah. And yesterday we discussed the units of concentration, so a good unit is molecules per micron cubed. Yeah. So the concentration of DNA will be like 1 molecule. Well, this is the concentration of the gene. I'm not talking about the bulk concentration of the genome, but just how many copies of the gene are there inside a cell. At any given time, there's usually 1, but there sometimes can be 2, right? Can somebody tell me why? Because just before cell division, you have to make 2 copies of the thing, right? So sometimes there are 2 copies of a gene, okay, but I'm not going to discuss all that now. So there's some concentration of DNA, and the rate at which you make this is some alpha times that concentration, right? So alpha is the per gene copy rate of making something. Yeah. And what you want to do is write down something like this, right? So you say d m dt is equal to some alpha times concentration of DNA, that's the creation rate, okay, minus some gamma. So gamma is a rate constant, alpha is a rate constant, these are not rates. So they need to be multiplied by concentrations in the first order chemical reaction, right? So it will be gamma times m. Okay, and you've already seen an equation like this in a different context when we're talking about population growth and so on, right? So the fact that death is proportional to the number that are already there. Okay, so if this is the setup, now for now, since the concentration of D is constant, yeah, and in our units the concentration of DNA is 1 copy per cell, 1 copy per cubic micron, I'm just going to set this to 1, right? And 1 molecule per, and I'm going to use small m to represent concentration of mRNA, but I'm going to again cheat a little bit, right? Concentration of mRNA is the number of mRNA molecules per cubic micron, and I'm going to imagine for the rest of today that the cell is not growing, its size is exactly 1 cubic micron, and so this concentration is actually equal to the number of mRNA in that cell. Okay, so I'm not using molar units and so on and so forth. This is going to be important. So this is going to go to actually the number of mRNA. And so mRNA molecule is actually created and then it can get destroyed, and it happens in discrete units. Okay, everybody happy with this? Any questions? This is the setup. So the difference from your traditional chemical reaction world is that traditionally these are just concentration units, they can be continuous numbers. Okay, but when you look inside a cell, the number of mRNA copies in a single cell has to be discrete. Okay, now let's take this equation and just write it using these variables. Right, already you should start to get worried. You start to get worried because if m is really the number, then what does this equation even mean? Right, dm dt assumes that little m can be a continuous variable. Okay, it's not, which is not what I just told you. Okay, so something is wrong with the way we're thinking about the system. It's not consistent, and so we have to start thinking about a better way to look at it. So as usual, the best way to start is just to try and build some intuition for it. So try and understand if I looked inside a bacterial cell, and these days we can do these experiments, you can actually count how many mRNA molecules there are in a single cell as a function of time, and you plotted it, what would it look like? This is time, this is m, and what would it look like? Let's say you start with 0, right? 1, 2, 3, and so what would this look like? What's the first thing that will happen? You start off with no mRNA, what's the first thing that will happen? Raise your hand, I see a lot of you nodding and so on, but I don't know what you're thinking. What's the first thing that should happen? Yeah. Yeah, there's no mRNA, then what happens? There is DNA. This is the setup, right? I'm just starting with all this, but I'm starting with an initial condition with no mRNA. So what's the next thing that happens? 1, okay, when does it happen? When will it come? After? At some time point. Okay, fine, so you go make 1. Then what happens? Will you make another? How do you know how many you're going to make? At what point does it stop making something? Just think about it. Just imagine a cell and think about what's going to happen here. Okay, so let's start. Good. So we have these rates here, right? So let's start just looking at this equation and seeing if we can get some guess at least for what should happen, right? We know it's wrong. We know this can't possibly be the correct equation, but at least we can, if it looks like a chemical reaction, something about this must be true. So what's the solution to this equation? You've already derived this a couple of times. I think Mandar derived it day before yesterday. So what's the solution to this equation? It's easy to solve, but let me just write it down. So let's say you start off with 0 mRNA, then you'll have m of t is equal to some alpha over gamma 1 minus e to the minus gamma t. Okay, you can take my word for it, or you can plug that back into this and you can test that it actually is the solution to the equation. Right? It's a fairly simple equation to solve. Yeah. So that is the solution to this equation, which we know can't be correct, but let's use that as a starting point. And what does that curve look like? It looks like this. Right? It goes up to a value alpha over gamma, and it takes roughly a time scale of 1 over gamma to get sort of roughly halfway there. Okay, that's what this equation says. So now, do you want to revise what the actual number of mRNA in the cell will look like? Since we know that it can't be continuous, it has to be discrete. What does it look like? So when should the first one be created? Will the first one be created here? How long will you have to wait before the first one is created? Here? Instantly? I'm just asking you to think. There's no way that you would know the answer if you've not seen this before, so it's fine if you don't know, but I want you to guess. If you don't guess, then you won't have any basis to compare with the actual result, right? So I want you all to guess. What will the actual number of mRNA look like? Just guess. I'll wait for a few guesses before I move on. Is the question clear? The question is that this curve can't possibly be the answer, right? Why? Raise your hand, I'll come to you. Why can't this curve be the answer? Yes? Because it's discrete. You can't have 1.5 mRNAs. You can't have 3.7 mRNAs. Okay, so that curve is wrong. The curve is telling us something. So based on that guess, what do you think the actual answer is? Just guess. What should the real number of mRNA look like? But you must have guesses. You can't not have a guess about something this basic. It's a very simple thing you can just guess. Right? You may not get the right answer, but I want you to put some ideas forward. Okay, alpha by gamma is a number which is approximately 10 in this case. Yeah. Just guess. I mean, don't. Why is everybody holding back? Somebody want to come up and try? Okay, somebody come up. I need 3 people to come up and draw this now. I think Kavita had the right idea yesterday. So can I have 3 people from this side and 3 from this side? Again, we've segregated for some reason. 1 person from each row. Come forward. 1 from each row. Come on. And on this side, 1 from each row. Go ahead. Come on. Don't worry, you're going to be on camera. No, I'm very serious. If you don't engage and have a guess beforehand, then you're just going to take what I say as the right answer, and it won't surprise you, it won't conflict with anything you knew, and you'll forget about it tomorrow. If you come up and have a guess to start with, you might have a shot of remembering it for at least 1 year. Right? That's the level of difference that will happen if you engage with the question and have a guess before you start versus if you're just going to take what I say as the truth. So I need 1 person from, I'm very serious, come on, 1 person from each row, from both sides, come on. From each row, second row. It doesn't matter who, it's very simple, okay. I want you all to draw diagrams of what you think the answer is going to be. Each one is going to get a little blob, here. Second row, come on, no, I'm very serious. We're going to waste 15 minutes just getting people on stage, then you're going to lose out on what the full lesson is. 1 person from the second row, 1 from the third, and 1 from 3 rows. I'm very serious, come on. If you're not willing to come up, I'm not willing to teach. I'll leave the room. If you're not willing to do this little thing of coming up, I'm not going to teach. I'm very serious. Okay, fine, we can close up. Okay, I guess that's it.
This is not just about somebody standing there and popping something to you. You also have to. This is serious.
Come on, guys. I'm not going to put in the time to teach you if you're not putting in the time to just do these small things I'm asking. Right? We take a lot of trouble to prepare these lectures, so we need you to participate. So please, can we have 1 from this row, up there. This is a small row, you got lucky. 1 from this row, up front, come on. No, this is not a joke. This is extremely serious. Go ahead. You don't have to discuss. It's not a democracy.
It is okay to be wrong.
You can be wrong. 1 person from this row and 1 from this row. You're all hoping I'm not coming to you, but one of you needs to get up. I'm not even kidding. I want one of you to get up and come. Okay, good. From this row, please. To the front. Okay. This is actually very good. No, don't solve the equation. I just want you to draw curves. I don't want you to solve equations. I don't want you to show off nothing. I just want you to draw. It takes 5 seconds. Just draw a curve. No equations. I just want you to guess what the curve will. No equations. I'm sorry. No symbols. No equations. Nothing. I just want you to guess what that curve will look like. Okay? There's lots of chalk. We're still missing maybe 1 more person from this side. Okay, this much is enough. I don't want you to get the right answer. I think everybody is mistaken and thinks this is a test. I just want you to draw what you think it will look like. It should take less than a second to do it. Okay, that's done. Okay, you're done. And good. You're almost done. Keep going. Don't look this. The answer is not on the stage, right? I'm just asking if a cell is making a molecule and it's destroying a molecule, and the molecule number has to be an integer, what will the number of molecules look like over time? Just draw it. Okay, that's good. Scott free, good. Thank you. And you're also done. Good. Okay. Okay, that's so you're also drawing roughly the same thing. Okay, but where are the numbers? Where are the integers? 1, 2, okay, 3, okay, fine. Good, that's fine. Yeah, and that doesn't answer my question, right? Those are not discrete values. They're not 1, 2, 3, 4, 5 values, right? So just finish with the. Okay, don't copy what somebody else did. Think about the question and think why you're drawing what you're drawing. You're in a cell, the cell is making a molecule and that molecule is also being destroyed. How many molecules would there be as a function of time? right answer doesn't matter. Don't look here. Just imagine the situation in your mind. Right? Just draw what you think will happen inside the cell. When will the first molecule be made? After 1 second? After 10 seconds? So those dots mean what? I mean, people have put dots. So what is the interpretation of that dot? One molecule is made. Okay. Well, second dot means? So that should be one higher. So the second molecule is made. Okay. So I think that's time. Okay. You can relax and go back. So look, guys. So the question I asked is not a complicated question, right? In the sense that you understand the words I've said, right? So it's not good if you're not thinking about the word questions. I'm not asking you to solve some crazy mathematical equation. I'm just asking you to speculate based on no information or whatever you know from any other thing you might have learned what this might look like. Yeah. So, if you just look at a formula, you don't know whether it will surprise you. You don't know if that's what you expected because you're not going in with any expectations. Right? And that's a very bad way to learn. Right? You have to try. The goal of this whole school is not for you to remember how to calculate these formulas. Right? It's about engaging with a model, making a model yourself, building. It's a creative process. Okay. So, I guess these three were sort of carbon copies of each other, which I find quite disappointing, but that's okay. Yeah. This one is different somehow, but I guess it's just uses a different type of. So 1, 2, 3, 4, 5. Is that right? That's okay. So those two are also the same. And this one is actually rather different, right? It's going up and down. So this is interesting for me. I'm just expanding what's drawn here. Okay. And here, I'm assuming this is what was meant. And that is roughly the same as this. Okay, so let's leave that aside. So let's think about it. What is the interpretation here for the person who made this? Who drew this one? Yeah, what's the interpretation here? Increasing. At some point it just... And what happens to the mRNA then? They just stay. In this case, let's say 1, 2, I mean it's a good guess, 3. So after you made 3, what happens in the cell? You're saying that those 3 are there and nothing else happens. Yeah, but here you said it hits saturation. So what does it mean? But where's the destroy here? Nothing's been destroyed. Here, this is interesting. Here it's been destroyed. Here it was made. So here 1 was made, 2 was made, 3 were made. 1 got destroyed. Which one we don't know. Another got destroyed. Then 1 was made, and so on. So here there's something going on. Here there's, I think in the back of your mind there is some idea of being destroyed because you said there's saturation, right? But where are the mRNAs being destroyed here? Here there's only creation, right? Yeah.
One more point.
Yeah.
Everybody is discretized time in the sense that mRNA is created at 1 second and at 2 seconds.
Yeah, very good. So there's this also. They seem to have been created at precise intervals over time and in space. Very good. Okay, well, this is good. This is good. So in the back of your mind, you're thinking in the first second one was created instantly, and the second one was created, and so on. So yeah, I hadn't noticed that. Good point. Okay, so that picture is not correct because it doesn't capture this process, okay, of an mRNA being removed. Okay, many people, when I ask this question, they would. That curve is similar to drawing the following thing here, right? Right, it's drawing sort of a staircase pattern that matches the chemical kinetic sort of expectation. Okay. Now, the difference between this and this sort of staircase diagram will be evident in just a second, based on Rahul's comment. If I wanted to really keep this as a staircase where I go up in 1 unit at a time, then I'm going to have to delay the time intervals between which mRNA are created. Now, since there was some difficulty in drawing it. I want you all to understand what this curve means, right? If I go up by 1, what does it mean? It means one molecule was created, right? So what's happening to the time intervals between creation events? Here, the time intervals are increasing. Why are they increasing? They're increasing because we want to stick to that curve, right? For no other reason, right? Good, the concentration is increasing. From the equation we know that because the concentration is increasing, this curve will saturate. That's true. And to try and capture that idea, but then also add the fact that it's discrete, we have to add this funny notion that the time interval will be different. Okay, that's what this curve predicts. That's not what this predicts, and we'll just get to that in a second. How does this cell know that there's that much mRNA and then to wait for a long time before it makes the next one? How can this curve actually happen inside a cell? Okay, there could be some feedback. So somehow the cell is reading that there are 5 mRNAs, then 6, and when you start to get to close to 10, then it's coming back and saying, don't make any, you have to wait much, much longer, right? Now, one could imagine that kind of thing working, but none of that is in this model, right? We used this model to write this equation without any feedback. But you're right, there could have been feedback, right? You could imagine a crazy situation where a cell counts how many mRNA there are, and then it starts the clock ticking, and it says if there's 8 mRNA, I'm going to wait 10 seconds. But if there's 9 mRNA, I'm going to wait 30 seconds. Right? You could imagine some crazy thing like that going on. But none of that was in this equation, and still the equation predicted a curve like that. Right? So somehow that curve captures something real about the system, but the answer can't be that it looks plus some differences, because some cells would have left and some cells would have come. So what should I write down here? That Ck in the next time interval is Ck in this time interval after you take care of all these guys that moved. Okay, so what should I write here? Just read it out and so how many cells would have been added to this bin? How many cells would have got K mRNA now that didn't have K before? Sorry, slowly raise your hands, I'll come to you. You all, one person at a time. I can write down what anybody tells me. Yeah. Good. Perfect. Right? It's these two things, this one and this one. Right? And then you have to put minus, right? And then do the other one, right? So minus Ck alpha delta T minus Ck K gamma delta T. Okay? That's how much you would have. Yeah. Now I'm just going to move things around, right? So I'm going to write Ck T plus delta T minus Ck T divided by delta T, right, is equal to, and I'm just going to write these terms. So it will be minus Ck alpha minus Ck K gamma plus Ck minus 1 alpha plus Ck plus 1 K plus 1. And this is a little bit confusing, and I again want you to unpack this. In the old way of thinking, alpha was the rate of creation, right? So you keep associating that with going up, and gamma is the rate of destruction, so you keep associating that with going down. But in our new way of thinking, both alpha and gamma can increase the number of cells in this bin, and both alpha and gamma can decrease the number of cells in this bin. So they don't occur with the same kind of signs as you're used to. Okay, alpha and gamma have very different signs, and it's very important to keep track of each of these different terms. So the left side is usually written as what, if you know your calculus? Yeah. So now it's sort of dCk dt, sort of, because again the C is also a discrete variable, right? C is the number of cells with that much mRNA. Yeah. But in this case, although the number of mRNA in a cell is very small, the total number of cells in my experiment can be ridiculously large. I can have 10 to the 9 cells, right? And with that many cells, I can easily pretend that C is a continuous variable. Okay? And I'm going to do one final thing. I'm going to divide every term of this equation, right, on both sides by 1 over the total number of cells. I'm going to divide by the total number of cells. I can do that, right? Because the left and right side I'm dividing by the same numbers, the equation is still correct. Now when I do that, you'll notice that the C total goes into every term. This becomes this over C total, this over C total, this over C total, this over C total, this over C total. Okay? So now these terms represent what? They represent the fraction of cells out of the total number that have a certain amount of mRNA. Right? Not the total frequency, but the fraction. So this is like a normalized histogram instead of a full histogram. Okay? Any questions about that? You can work in both ways of thinking. You can think that the C's represent the total number of cells, or you can represent as C over C total, which you can call P if you want, like the fraction of cells that have a certain number. Right? And I'm going to do that here. If I divide both sides, then I get another equation where C's are replaced with these things, which let's say I'll call it P sub k. Fraction of cells with K mRNA. But it's a normalized histogram. And finally then we get this equation, which I guess I'll write, let me write it up here. Can I erase this? We get this equation, which is a very nice equation, right? dPk dt is equal to minus Pk times alpha plus k gamma plus p k minus 1 alpha plus p k plus 1 k plus 1 okay. I've just taken this, I've replaced the left side with a derivative because I can do that, and I've just replaced the C's with P's. The C's are the total number of cells, the P's are the fraction of cells. That's just, you can do that just by dividing by the total. Okay. So that equation is an important one. I'm going to erase this. Right, if you want to derive that equation, you don't have to remember everything. All you have to do is to remember this little diagram, right? And convince yourself of what's coming and what's going. If you don't remember all the terms, and just work through it. It doesn't take more than a couple of minutes, and you'll get the correct equation. Okay, so this is an amazing step, okay, because we had just started off with this silly equation, right? And then we realized that this term in this equation is not a rate, but it's a probability per unit time. This term in the equation is not a rate, it's a probability per unit time. Once we did that, a few very interesting things happened. The m no longer became the variable, right? M just is a label. What became the variable are the height of each bin of the histogram. Well, that's the first important thing that happened. The second important thing that happened is we went from one equation to how many equations now? How many equations are here? Not number of cells, not k equations, not number of cells. I've already normalized the number of cells. This is the fraction of cells, right? Number of possible number of mRNA, which is potentially infinite, right? So the number of what happens to cells with k mRNA depends on what happens with cells with k minus 1 mRNA and k plus 1 mRNA. You can't stop. Right, on the left side you can stop at 0, but on the right side it keeps on going. Okay, this is astonishing. So we thought this was easy, and suddenly we get infinitely many equations. Everybody see that? There's an equation for dp0 dt, right, which is minus p0 times alpha plus 0 times gamma, right, plus p minus 1, which is nothing, right, plus p1 times 1 times gamma. Then there's an equation dp1 dt, right, is minus p1 times alpha plus gamma plus p0 alpha plus p2 times 2 times gamma, and so on. There is a large number of equations. Okay, so and you got to solve the whole thing. Okay, so this is nice in the sense that it finally has approached the kind of complexity we want, because we always knew that the thing that was changing was this histogram, and in principle the histogram could go, quite far, right? So to capture the histogram, we always knew that we'd have to have a lot of equations, and we have now. So we've written down the correct equation. Now the next step is to try and extract value from that equation, and I'm going to do that before we take the break, and I'll return to this in the afternoon session. Once we have an equation like this, so all of you know that if you write down differential equations and you want to just get an idea of what it does, one of the things you can do is what? So differential equations are complicated, so you get rid of the differential part, right? How do you do that? But if you don't want to worry about ddt's, what do you do with those? So you've already done this many times, and just this past week I've seen many people do it, right? If you have a differential equation and you don't want to do the differential part, what do you do? Study steady state, right? Just set it equal to 0. But that's one thing you could do. And setting it equal to 0 means that you're really waiting long enough so the histogram doesn't change anymore. And the histogram not changing anymore is actually a little bit tricky, right? Although individual cells are constantly jumping back and forth between the different bins, they are matched evenly. So the flux is all exactly matched, so the histogram shape doesn't change anymore. So that's the first thing we're going to do, right? we're going to try and set everything equal to steady state, right? So, and let's just see what happens. Let's just see what happens. So let's do that. We'll do it term by term, right? So we get. Oh, okay, I should have written all this down, right? So minus p0 times alpha plus 0 times gamma plus p minus 1, which is 0 times alpha plus p1 times gamma is equal to 0. Okay. And then we get minus p1 times alpha plus gamma minus p1 times alpha minus p1 times gamma, that's these two, plus p0 times alpha plus p2 times 2 times gamma is equal to 0. And we'll just do one more step before we close. Okay, minus p2 alpha minus p2 times 2 times gamma plus p1 alpha plus p3 times 3 times gamma is equal to 0. Okay. So we're now going to start trying to work this out, right? So the best thing to do, so the problem is that so every one of these equations you need to know the value of p to the left and to the right to solve it. So this is an infinite collection of equations again, right? So we need to think about things a little bit, right? So let's try and make a ladder. Let's try and work out all the values of the variables in terms of the earlier ones, right? So we know that p must be 0 for minus 2, minus 1, right, minus infinity. You can't have cells with minus number of mRNA. So let's keep those as 0. Let's keep p0 as unknown. We don't know how many cells have 0 mRNA, and try and calculate p1 from that, right? So from this equation, we find that p1 is equal to what? Alpha over gamma p0. Isn't that right? Okay, so we know p1. Now according to this equation, right, p2 is equal to p1 alpha plus p1 gamma minus p0 alpha over 2 gamma, right? So then we're going to have to plug in p1 over here. So let's do that, which is alpha over gamma alpha p0, right, plus alpha over gamma gamma p0 minus alpha p0 over 2 gamma. Right. So the gamma comes here, this gamma gets cancelled, and the gamma comes here, the gamma comes here, and there's a factor of half. Right? These two cancel, and so you get half alpha over gamma squared p0. Right? And trust me, if you work out p3, you get p3 will be 1/3 times 1/2 times alpha over gamma cubed times p0, and so on. Right? I mean, it's just mindless algebra, and you can do it. Okay. So just by eyeballing it, you know what the answer is, right? You know that pk is 1 over k factorial, right, times alpha over gamma to the power k times p0. Right? This just drops out of the calculating this infinite ladder of equations. Right? And why is this p0 still sitting there? Because we couldn't solve for p0. We had to start somewhere, so we started at the left side. So what do we do with p0? How do we deal with it? But this is where we come back to the idea that what are the p's? The p's represent the fraction of cells that have k mRNAs. So the p is a histogram, and it's a normalized histogram. If it's a normalized histogram, what do we know about it? Okay, so the sum from k is equal to 0 to infinity p sub k, which is the sum from k equals 0 to infinity p sub 0 times 1 over k factorial alpha over gamma to the k is equal to 1. Right? That's a normalized histogram. So anybody know what this is? E to the power alpha over gamma. Good. Okay. Times P0 is equal to 1. And therefore, P0 is equal to e to the minus alpha over gamma. Okay. And this is the full expression for that histogram. Yeah. So stare at it. Let's try and understand what it looks like. It depends on what? The k is not a parameter. The k is the label of which bin you're talking about. Right? The only parameter in the system, the only parameter is this alpha over gamma. And what is alpha over gamma? Remember what it was? It was the steady state value in the old way of thinking. Yeah? Whereas now, it sort of shows up here in an interesting way. So this distribution has a name, and you saw it yesterday, and this evening, this afternoon, I'm going to show you all the ways of thinking about this, right? So generally, the shape of this distribution 0, 1, 2, 3, and so on. How many RNAs will have? How many cells will have exactly 0 RNA? You just plug it in here, right? You put k is equal to 0. What is 0 factorial? 1, right? So alpha over gamma to the 0 is 1. So the number of cells with exactly 0, the fraction of cells at exactly 0 RNA is e to the minus alpha over gamma. And that's really interesting, right? So it says that if the expected number of RNA is very big, because alpha over gamma is in our old way of thinking how many RNAs you wanted in the cell, then the number of cells with exactly 0 RNA is smaller and smaller and smaller. It kind of makes sense. On the other hand, if alpha over gamma, suppose gamma was 1,000 and alpha was 10, right? Then what is the expected number of mRNAs? Right? 0.01. What does it mean to have 0.01 number of mRNAs? So what it really means is that most of the cells have no mRNAs, and some cells will have 1, and so on, right? So if alpha over gamma is very, very small, close to 0, then most cells will have 0 mRNA. So if alpha over gamma is very small, this is what this curve typically looks like. Small alpha over gamma. If alpha over gamma is sort of big, this is what the curve looks like. Okay. Generally, the peak of the curve is sort of at what we had guessed earlier was the mean number of RNA, was the steady state number of RNA, alpha over gamma. Okay. And these kinds of things can be experimentally measured. So one final thing I'm going to do before the tea break. So that's one thing we were able to do, which is to find a formula for the steady state distribution. Yeah, can I erase this? Okay. Now we want to do something slightly more sophisticated, and since we've reached this and I do have time, I was wondering whether to do it or not, but I'm going to go ahead and do it. I always make a mistake here, so I want you guys to watch me and make sure that I don't drop my terms, but we're going to try and do this, okay? I want to get a formula for the mean of this histogram as a function of time. Right? So at every point in time there will be a histogram, and I want to find a formula for the mean as a function of time. I'm not going to go to steady state. I don't want to solve all the equations. I just want to find some way of understanding what the mean value of the histogram will be as a function of time. And remember what you said, if all the cells start with 0 mRNA, then the initial histogram is just a huge spike at C0 or P0. And then over time the histogram will become fatter and fatter and keep on moving this way as cells get more and more RNA. and the mean of that histogram is going to keep on moving. How can we use this equation to understand what the mean is doing? We just have to define the mean, right? So what is the mean value? Well, so in this case, so I guess I really should have used m instead of k, and I don't know why I did that, but okay, fine. Right? This m, that k, they're the same label. I don't know how we sort of lost track of it. Yeah. So what is the mean value of k? If you know the probability distribution of k, you can easily get the mean, right? We know the formula. What is it? The expectation value of k. Yeah. So, well, let me call it m, right? Good. Now I remember why I did it. So m is my mRNA number, and it can take on values k, k minus 1, k plus 1, and so on, right? So the mean mRNA number is sum from k is equal to 0 to infinity k p sub k. Yeah, that's just the definition. So if I take this equation, I can make an equation for the mean. Right? How do I do that? I take the whole thing and I multiply it by k. Okay? And let's hope for the best. Right? So on the left side, I'm going to do k dpk dt. On the right side, I'm going to get minus k pk alpha plus k gamma plus k p of k minus 1 alpha plus k plus 1, sorry, p, yeah, that's right, k plus 1 p k plus 1 gamma. Did I do this correctly? It's even at this stage I can mess up this calculation. Okay, so I've just added k to both sides of this equation. So I get k pk alpha plus k gamma, I get k pk minus 1 alpha, and here I get k times k plus 1 times pk plus 1 gamma. This is all fine, right? And now what I do is I sum from k is equal to 0 to infinity both sides. Okay, so what I get on the left side is d dt of sum k p sub k. Right? And this is the thing we want. Yeah? And on the right side, what do I get? This is actually going to be pretty complicated, right? So I'll write out all the terms separately. I get sum k is equal to 0 to infinity, okay, minus k p sub k alpha, and I get, all right, let me do minus alpha, and I get minus gamma sum k is equal to 0 to infinity k squared, is that correct? P sub k, is that correct? Is that fine? You guys can see better than I can. Okay, and here I'm going to get plus alpha sum k is equal to 0 to infinity k p k minus 1, okay, and I'm going to get plus gamma sum k is equal to 0 to infinity k k plus 1 p k plus 1. Is this correct? Yeah. Now the thing is, the left side is the thing we want. The left side is the thing we want. Okay. But the right side looks like a bunch of things we don't really like, right? So there's this thing we understand. This is the expectation value of k squared, right? But what is this guy? Some k minus 1, there's all kinds of funny things that happen. So now let's do just a couple of tricks just to wrap up in time. What was the value of pk for any value of k that's negative? 0, right? So I can replace all this k is equal to 0 to infinity with k is equal to minus infinity to infinity, right? Because all that's adding is a bunch of 0 terms. Everybody happy with that? Nothing went wrong here, right? I've just written exactly the same equation, remembering that p of anything negative has to be 0, right? Now, the other thing you can do, since I'm summing over all of k, I can just shift the label around, right? I can sum from 1 to infinity or from 2 to infinity. I mean, so it doesn't matter if I add a constant to k, right? So I'm just going to change the label. right? This is k of p k minus 1, but it's summed over all of k, right? So this is actually equal to sum from k is equal to minus infinity to infinity, right, of k plus 1 pk. These two are the same thing. I'm trying to do something and I'm just hoping for the best, right? I don't know. See, I know what I want on this side, but on this side it's a big mess. But I'm hoping that I can at least get rid of the k minus 1s by replacing them with k's, right? So everybody happy with this? This term and that term are the same. If you want to think of it differently, just replace k with j plus 1. J plus 1 is equal to k, right? And do j is equal to minus infinity to infinity. And then I might as well call j is equal to k, right? So that's what I did. K plus 1 pk, right? And this is equal to gamma sum k is equal to minus infinity to infinity of, there's a k plus 1 here, I want to make that a k, so I'm going to make these smaller. So it will be k minus 1 k pk. Okay. Now the right side is actually something reasonably manageable, right? So if I keep track of the whole thing, is equal to, if I keep track of the whole thing, you get alpha times this m. That's all that is. Okay, let's just keep track of it, right? So you get alpha times sum k p sub k. I'm no longer writing the limits because it doesn't really matter, right? And then there's an alpha here, so this minus alpha times this, plus there's an alpha term here, alpha times this is k plus 1 pk, right? So the first term of that will be sum of k pk, and the second term of that will be sum of pk. I've just split the alpha plus 1. Okay, that's this guy. I'm running out of space, but okay, I'm going to crawl underneath here. These two, and finally those, what do we have? We have the minus gamma sum of k squared pk. I'm going to rewrite this on top, so don't worry. So that's this term, and then you get plus gamma k squared pk that you do get, and then you get minus gamma sum of k pk. Okay. Now when all the dust settles, these two cancel, these two cancel, but you're left with two terms that don't cancel. So what you have is this equation. What is alpha times sum of pk? What is the sum of pk? 1. So this is just 1. And what is gamma times the sum of k pk? Gamma m, right? So you get this equation. Okay, so that's pretty cool. That's pretty cool. So once all the dust has settled, that original equation did have some meaning. That original equation, as some of you had guessed, really did represent, as you said, the expectation value of this curve. And there's a reason for that. And maybe I'll just mention it for those of you who are wondering. If any of these terms, if all the terms here are either constants or they depend linearly on the variable, there are no higher powers, then the equation for the expectation value would be exactly equal to the traditional chemistry equation. But if for some reason, you get some m squared term, somehow it's a bimolecular reaction for mRNAs decaying or something like that, right? As soon as that happens, this whole business becomes much more complicated. And the actual expectation value is no longer equal to the traditional one. And so as soon as you bring noise into it, funny things start to happen. It might be very close, but it won't be exactly the same. In this case, it's exactly the same. Okay. Final thing. Final thing. let's just verify that this equation matches this equation. Right? How do we do that? This equation represents the steady state histogram. This equation represents the time dependent mean. How do we check that they make sense? I find out the mean when this is in steady state, and I check explicitly whether that's equal to the mean of this. Okay, so we have 5 minutes, let's go ahead and do that. So I expect that in steady state, m is equal to alpha over gamma. Right? Okay. So let's verify that. How do I calculate the expectation, the mean of this, right? So I want sum of k pk, which is sum of k is equal to 0 to infinity, alpha over gamma to the k over k factorial e to the minus alpha over gamma. Right? How do I do that sum? Seems pretty complicated. Okay, so this is k times k minus 1, and then sure, you can split it, but can you do the sum then? Right. So this here you can use a little trick. Okay. So I'm only doing all these tricks because I do have 5 minutes left, and it's nice to finish the thing. All the big lessons from this morning are over. Right. We took a very simple equation, we made an infinite ladder of equations, and then we understood that that's happening because of randomness, and individual cells are jumping up and down, and now we have a picture of a histogram that's changing over time. Right. So all I'm doing now is just dotting the i's and crossing the t's. Right. So it doesn't matter if you're not following this 100%, the last bit. So there's a little trick you can use. Right. So let me just set alpha over gamma is equal to mu, just to keep the notation simple. Right. So you know that 1 is equal to sum of mu to the k over k factorial e to the minus mu. Right. That's how we normalize the histogram this way. Right. We knew this. Right. So now you can do a trick. Right. You can do d mu of this thing. Okay, just for fun. Right. And so what happens when you do that is equal to sum of, and this thing will be, it's product rule, right? So you'll get two pieces. You get minus e to the minus mu to the k over k factorial, right? And then you get plus k mu to the k minus 1 e to the minus mu over k factorial. Okay, and the reason I did this is because this is looking very much like that. Not quite, but very much. Okay, and this must be equal to 0 because the original thing was a constant. Dd mu of the left side would be 0, right? So you can then split that up. So then what you find is sum of e to the minus mu to the k over k factorial is equal to, and then this thing is not quite something we're happy with, right? Here the difference between here and there is that the mu has a different power, but that's very easy to fix, right? So I can say it's 1 over mu times sum of k mu to the k over k factorial e to the minus mu. Yeah, I'm just taking the same terms. What is this? That's just sum of p of k. This is just 1, right? And this is that expectation value of m, I guess. Right? So we do find that m is equal to mu. Mu goes up and the other side comes down. Okay. Now, if you guys are sticklers for punishment, we can use the same trick to find out what the variance of this distribution is. Shall we go through with it, because we only have 30 seconds left? it's going to cut into your tea break. If you want to, so how many people want to see? It'll take maybe 3 minutes. Okay, you want to see it? Okay, fine. Okay, so let's do it. Right? So we've now verified that the mean part is correct. Right? Now we're trying to do the variance part. So it's tough, but let's go for it. Now there's a little trick with calculating variance of something. So it turns out that the variance, this is the variance, right? If you expand it, what do you get? You get x squared plus mu squared minus 2 mu x, right? Which is x squared plus mu squared, but mu is just a constant, so averaging it doesn't do anything, right? Minus 2 mu times x. So this is just equal to mu, right? So you get x squared plus, so minus mu squared, and mu is just equal to the mean of x, right? So there's a very nice thing that you should all probably remember, which is sigma x squared, which is just what we derived, is the mean of the square minus the square of the mean. Right? This is a general thing, right? So if you remember this, you can easily calculate variances without too much trouble, right? So we've already calculated. So if m can take on values 0, 1, 2, k minus 1, k plus 1, whatever, and then we do the histogram, then the expectation value of m we just calculated was alpha over gamma, which we're calling mu. Now to calculate the variance, we have to calculate the expectation value of this k squared. So let's do that. So sum k squared p sub k is the thing we need to calculate. I'm really sorry about this jumping back and forth between m and k. It's one of those things which, you know, the name of a variable is different than the values it can take. You know? So sometimes I'll just call it expectation value of k, sometimes I'll call it expectation value of m. So I need to calculate this. So let's write it out. So this is sum of k squared alpha, or just mu to the k over k factorial e to the minus mu. Okay. And this we're going to have to, unfortunately, take 2 derivatives to figure it out. Okay. So let's do that. If you help me out, we'll get to t faster. Right. So let's start from the beginning. I'm going to use all this space. So we have 1 is equal to sum of mu to the k over k factorial e to the minus mu. And you do dd mu, then you get 0 is equal to the same thing we did earlier, sum minus e to the minus mu to the k over k factorial plus sum of k mu to the k minus 1 over k factorial e to the minus mu. Okay. And now we do dd mu again. We get 0 is equal to, and this is going to be fun. Let's see what to do. So, okay, the minus sign comes out. Again, you get sum of e to the minus mu. You get the same thing again for this guy, e to the k over k factorial minus sum of k mu k minus 1 over k factorial e to the minus mu. That's just this guy splitting up. Then you get that guy. You get minus sum of k mu to the k minus 1 over k factorial e to the minus mu plus this term k minus 1 over k factorial mu to the k minus 2 e to the minus mu. Okay. So I've just taken the whole shebang, right? The full derivative thing. This is just 1. Okay. This thing is equal to minus 1 over mu sum over k mu to the k over k factorial e to the minus mu. And this is just that. This thing, what happened here? Did I do it correctly? Is this correct? I did this by different, yeah, this is correct, right? This is the same thing again. These two look the same. And this thing is equal to 1 over mu squared, right? Sum of k minus 1 over k factorial mu e to the minus mu. Okay. and my arm is getting tired, and I also want tea, so I'm going to stop. I've taken you far enough to see that it all boils down to terms that involve the mean and the expectation value of k squared. Okay? So, when the dust settles, you will find that sigma m squared, which is the variance of the mRNA number, which is the thickness of this histogram, or the square root of that is the thickness of histogram, is actually equal to mu m. If you go through this whole exercise, okay, and I'll cover this in the evening, so you won't have to worry about it. You'll see it one more time. I just want you to notice that we derived something that looked like this yesterday. Right? We derived a distribution whose standard deviation is equal to the square root of its mean. Yeah, it's called the Poisson distribution. It's no coincidence because this thing is the Poisson distribution. Yeah, and so the reason this is nice, to summarize, I shouldn't have erased that equation. So to close the morning session, where does the deterministic behavior of chemical reactions come from in a tube? When we know that in a single cell it's so noisy, the same reactions happening in a big tube are not noisy. That is true for two reasons. The first reason is that the expectation value looks just like the chemical kinetic equation under various conditions. The second reason is that in real life, in chemistry in a tube, the mean number of molecules is like 10 to the 23. When the mean number of molecules is 10 to the 23, the standard deviation will be square root of 10 to the 23, it's about 10 to the 12, and the relative error, the standard deviation divided by the mean, will be 10 to the minus 12. So this histogram will be, insanely narrow and look just like a deterministic thing. Okay? So either you want to think of the deterministic law coming out of the expectation value, or you could just think of the histogram becoming narrower, narrower, narrower until you can go back to just pretending that the whole population is just described by the mean value, because they're all just centered around the mean, right? And those are two perfectly consistent ways of thinking about things. That's why chemistry actually works using these chemical kinetic equations, but when you unpack it, it's much more complicated underneath. Yeah. So I'll stop. What we're going to do in the evening is build more intuition about exactly the same distribution for gene expression, and I'm going to describe some experiments we've done to understand what really happens in single cells. Okay.